Hello, welcome to GPU Teaching Kit. We are at the Module 9, Parallel Computation Patterns. We will be covering Lecture 9.2, a basic reduction kernel. The objective of this lecture is for you to learn to write a basic reduction kernel in CUDA. We're going to study thread to data mapping. We're going to learn how to turn on and off threads, and we're going to study the phenomenon called control divergence. In this lecture, we're going to learn to write a kernel that performs parallel sum reduction. The design of the kernel is such that we have each thread to add two values in each step, and then all the threads will take steps towards generating a final sum. And through the steps, every step of the way, we will recursively have the number of threads in each step. And the whole computation will take log n steps for n elements, as we illustrated in lecture 9.1. And this requires n minus 2 threads for n elements. We will be assuming that we will be doing in-place reduction using shared memory. What we mean is the original vector is in the device global memory. We load the vector into the shared memory. So initially, the shared memory will hold a partial, will hold the original vector. And then we will perform all the operations on these same shared memory locations. We're going to be updating part of the shared memory location in each step of the computation. And in the end, we're going to have the final sum in element 0 of the partial sum vector. So the contents of the vector will be updated as we go, and that's why it's called the in-place computation. And this reduces global memory traffic because all the reading and writing of partial sum values will be done to the shared memory, and they will not be going out to the global memory. And because of this design, the thread block size of 1024 up to 1024 threads will limit the number of elements that we can process with this kernel to 2048. That is, each thread will add 2 elements. So we will be able to start with 2048 elements and using up to 1024 threads to generate the final sum. This slide illustrates the operation of the parallel sum kernel. So in this picture, we show the threads in the horizontal direction, thread 0, thread 1, thread 2, thread 3. And then we show the steps in the vertical direction, steps 1, 2, 3 in the picture. And we also show that the vector that will be processed by the threads, and we show them on top of the horizontal direction. So we have initially the vectors elements 3, 1, 7, 0, and so on. And we show that every 2 elements will be mapped to a thread, so that initially in the first step, every thread will be adding 2 original elements into a partial sum. And then in the second step, we will have the number of active threads. So we only have 4 partial sums to add for the next step. So we only need to have 2 threads. So in this case, thread 0 and thread 2. And finally, in the third step, we only need to add the partial sums 11 and 14 into the total sum of 25, and we only need to have 1 thread to do the work. So as we see, as we progress in the steps, we will have the number of active threads in each step, and every step of the way, we are updating part of the element. So even though we show these elements to be in the vertical direction, there are actually changes to the corresponding position in the original vector. So 3, 4, 11, 5 are actually all in the same shared memory location. We're just showing the time progression of that location in the through the algorithm. The design of the kernel that we showed in the previous slide assumes a naive thread to data mapping. In this mapping, each thread is responsible for an even index location of the partial sum vector. That is, thread 0 is responsible for shared memory location 0, and thread 1 is responsible for shared memory location 2. Thread 2 is responsible for shared memory location 4, and so on. And after each step, half of the threads are no longer needed. As we have shown in the previous picture, with each step, we only have half of the threads active compared to the previous step. And one of the input is always from the location of the responsibility. And as we have seen in the previous slide, each thread, when adding numbers, one of the numbers always come from its home location of responsibility. And that's the even index location. And then in each step, one of the inputs will come from an increasingly distance away. So for example, in the previous picture, in the first step, all the elements come from just the neighboring location. And then the next step, all the elements that are added by the thread come from 2 locations away from the location, and so on. So this slide summarizes the reason why we need to have that sync thread instruction. Once we finish the execution of the for loop for all the threads, this means that we have the entire section of the input vector reduced to one reduction outcome. And so at the end of the kernel, we only need to have one thread. We can just use thread 0 in each block to write the sum of the thread block into partial that is located in partial sum 0 element into a vector indexed by the block IDX. So this essentially assembles a new vector where every element is the partial sum produced by by one thread block, and that's why this array is indexed by the block index. And then there can be a large number of such sums if the original vector is very large. So for every thread block, we'll take 2 blockdim.x number of elements and reduce that into a single value. But if the original input vector is big enough, we can still have a large number of these partial sums produced by all the thread blocks. So if this output vector is very big, the host code may actually iterate and launch another kernel on this partial sum vector, and then reduce that into a single value. If there are only a small number of these sums, then the host can simply transfer the data back and add them together. When there are only 5, 6, or even 100, it's pretty easy for the CPU to be able to just run a sequential loop and add them together. So That's why, if the number of sums is small, it may not be worthwhile to launch another kernel and use the GPU to produce the next round of sums. Alternatively, we could also have the thread zero of each thread block to use atomic operations to accumulate into a global sum variable. This way, when all the thread blocks are done, we actually have the entire global sum. We don't even need to have another round of adding. When we have reasonably large block sizes, the execution time of the blocks will be reasonably large, and then so the frequency at which we're going to go and increment uh, the, uh, the global sum with the atomic operation may be infrequent enough so that it does not serialize the blocks in the as we discussed in the histogram lecture. This completes lecture 9.2 of the GPU teaching kit. Thank you.